paper. Oh. Okay. We're going to start the paper presentations on April when? 16th, right? Is that correct? Okay, so you'll have at least almost a month to prepare for your papers, which is good. And I will suggest that you meet your mentors as soon as possible. That'll help you plan better. Does that sound good? Okay, so today I'm going to cover the rest of memory robustness. Hopefully we won't take the full lecture, but that's a dangerous thing to say because I can always expand to the entire lecture. So let's see. So last time we started talking about memory robustness, and this was the other title for this lecture. We talked about RowHammer, which I will not keep hammering on you, no pun intended. And you've seen the paper. This time nobody's going to present this paper, but I'd recommend you to read it still. It's very interesting. Maybe I'll tell you the story. And we talked about the security implications of it. We gave some examples, and we talked about stories related to it. These are actually some papers that you may want to read if you're interested in this area. But this is the jog your memory of what we talked about. We talked about understanding RowHammer, and we have looked at a lot of data from the first paper and some other papers. This is the revisiting RowHammer paper. And we talked about some of the other papers also. We actually covered this paper and stopped at the end. I'm going to show that again. So understanding RowHammer is actually very important because RowHammer is a problem in any kind of DRAM chip, including HBM chips. HBM chips are high bandwidth memory chips that are used in essentially all AI infrastructure today. All of the AI accelerators, machine learning accelerators have HBM because it's high bandwidth, and you need high bandwidth to fetch the data at high throughput for these machine learning models. GPUs have all HBM, and RowHammer affects all of those HBM chips very similarly to it affects the other DRAM chips. The main difference of HBM and other chips is the interface. It's a much wider interface, and also where you put the logic to access the data. So internally, the array, the subarrays are very similar, actually essentially the same in all DRAM. What makes LPDDR different from GDDR, different from HBM, is the interface that you have to these chips from the memory controller. And also how you design the controller is different, of course, because different specifications are different. So HBM clearly has similar vulnerability, and we have some papers on that topic. There's more to be done in this area. One of the difficulties in this type of research is manufacturers try to hide as much as possible so that people don't figure out things in their chips that they consider are, let's say, secret. They think this may affect a lot of things in terms of their competitiveness, because this area, like DRAM, is also a very competitive area these days in terms of margins of chips, like how much you can pay or how much the chips cost, as well as the design of the chips. So it's becoming more difficult to actually get real data from the DRAM chips using the infrastructures that we have developed, because there are not that many infrastructures. For example, HBM2, HBM2E, they're supported by the FPGAs, but HBM3, there's no FPGA that has an HBM3 attached to it, for example, today. At least it's not publicly available. So it's very difficult to do these studies and discover what's going on in the very latest chips today. That's true for DDR5 also. There's no FPGA where DDR5 is connected easily. So we're looking for ways of actually building that infrastructure to discover more about more recent chips. Okay, so there are a bunch of papers, and these are some studies that actually were done to understand more about RowHammer. For example, there's a huge spatial variation in RowHammer. Can you actually understand how that spatial variation happens? Like which parts of a chip are more vulnerable than the others? And can you actually find ways to make future solutions more efficient? We talked about this very briefly at the end of last lecture, but there's a lot more. You can essentially write a full paper about this topic. This is actually a very dense paper that talks about the spatial variation in RowHammer vulnerability across chips. And Giray has done a lot of work on this topic. He's a faculty member at CISPA right now in Germany. And his dissertation actually looked at a lot of issues in understanding RowHammer and also developing solutions. So it's like a very comprehensive dissertation about RowHammer. Okay, we also talked about solutions yesterday, and we said that if you discover issues like this, you need to protect the chips that are immediately vulnerable in the field, and also hopefully you can develop better solutions in the longer term, because if you don't have very good memory controllers, you may have limited possibilities for the immediate solutions, right? If you cannot program your memory controller, if you cannot upgrade it, you cannot fix the problems, at least at low cost, right? So we discussed some of these solutions. This is a picture that you have seen in the last lecture, where we discussed different solutions. And I remember this room had this problem, I guess. Hopefully, maybe there's another one. I don't know. Okay, so we discussed that these two are the most, let's say, promising ones, because all of the others have some significant issues like error correcting codes or increasing the refresh rate. And we discussed that the key is basically somehow detecting the rows that are activated frequently, that are kind of aggressor or potential aggressor rows, basically detecting potential aggressor rows and making sure that they don't impact the potential victim rows. The solutions can be described that way, basically, right? So there's a detection mechanism. It's also called a tracking mechanism. How do you track the aggressor rows? Become important. Do you track them probabilistically? Do you track them deterministically? Meaning, do you have exact counts or do you not have exact counts? If you have exact counts, how do you structure the counts, etc.? There are many interesting issues in tracking over here. And then there's a mitigation mechanism, which is how do you ensure that the victim rows don't get damaged, right? And you could do that by refreshing the victim rows, or you could do that by ensuring that the aggressor row doesn't get accessed further to damage the victim rows. These are both good ideas, I think. Now, the devil is always in the details on how you implement these things. And you can implement all these mechanisms either inside the DRAM chip or outside the DRAM chip. This is a bit harder to implement inside the DRAM chip because throttling and access that is sent to the DRAM chip today is very difficult because we don't have a good DRAM interface. DRAM chip is supposed to obey everything that the memory controller says, right? We discussed this before. That's why having a better interface actually enables better solutions on the DRAM side as well. So DRAM can say basically, I'm not going to service this request right now because there's something important that I'm doing, for example, right? Okay, meaning RowHammer protection. Or I'm throttling you because I'm in danger of getting a bit flip in this region that you're trying to access, right? So that's the throttling part. Okay, so it's good to think about these mechanisms as tracking and mitigation. And tracking can be done probabilistically and deterministically. Mitigation can be done in refresh, throttling, or remapping, as we discussed. But remapping tends to be very costly if you don't have support from DRAM itself. Okay, so there's still a lot of solutions in the solution space, I think. There are papers, I'm going to flash some of them probably later, that are coming up at ASPLOS, for example, which I'm flying to tomorrow in Pittsburgh. That was the joke about Pittsburgh over there. So maybe we want one of your mentors to be there so that we don't have any issues with live streaming. Okay. And all of the solutions are part of a rich trade-off space in terms of cost, power, performance, and complexity. And maybe the security guarantees also, right? Now, we also discussed what manufacturers and also system designers did. They basically increased the refresh rates because the memory controllers were not, let's say, programmable. And this is not a good solution. We discussed that also, right? So this paper actually proposed 7 different solutions and said probabilistic adjacent row activation is a good solution. But we also said that as we also said in the last lecture, that as chips become more vulnerable, that sort of solution becomes harder to, let's say, make high performance. That was discussed in a later paper, revisiting RowHammer paper. But basically, people have been developing a lot of intelligent controllers. That's the key. That's what we suggested in this paper. People should be designing memory and the system together. And this comes with having more intelligent controllers, either on the DRAM side or the memory controller side, and better interfaces also, we argued, so that you can actually solve these issues much better. Okay. So we also discussed what has happened to RowHammer in 2020, 2026. We talked about revisiting RowHammer paper more recently, actually. I don't know if it was last week, but we learned that this was selected as the top picks in hardware and embedded security, which selects basically a handful of papers from these publication years, 2029, 2024, that has been influential in industry. And we've discussed that this paper analyzed the scalability of the RowHammer vulnerability to many generations of DRAM chips and also many different types of DRAM chips, and basically showed that things are getting worse because it's a technology scaling problem, right? As a result, finding a good solution meaning low overhead, low cost solution, is going to become more and more difficult going into the future. Now, these days, people are actually developing these solutions that we predicted will happen. So that's good. There are papers in top conferences that talk about some of these solutions. I'm not going to talk about everything here, but there's a rich body of literature that I'm going to flash that you can learn or also improve on. This is actually an exciting area. If you come up with a different idea, a different solution, people are very receptive to thinking about these solutions, publishing them, and also potentially implementing them. So this is an area where there's a lot of potential impact that can happen right now. Okay, so we also discussed that with this sort of analysis, you can change the belief in the community that the problem is solved. So the problem is solved can be proven by data, right? So if you provide data that is real, then you basically can challenge the problem is solved claim, right? I think I would argue that people should not believe things without data. That's a more appropriate way of doing things in science, right? If someone doesn't provide data, just they have a claim without any data, then that should not be believed. But unfortunately, sometimes that's what happens. Okay, so this is the top picks. If you're interested, you can read the news. I like this picture. That's the new RowHammer, AI generated. Okay, so we also talked about the trespass work, where we demonstrated that you can induce these bit flips in chips, DDR4 chips that are vulnerable to RowHammer, that are claimed to be not vulnerable to RowHammer. And we did that by reverse engineering the mitigation mechanisms. This is actually a very interesting area also. How do you reverse engineer what goes on in a chip without knowing what goes on? And we developed different methodologies, including the many-sided hammer attack, RowHammer attack. And we basically showed that this is still an open problem, and security by obscurity is likely not a good solution. So I still think security by obscurity is not fundamentally a good solution if people can figure out what's going on. And we're going to talk about that when we get to current solutions in industry. Because there are a lot of solutions in academia, but there's also a current solution in industry that we're going to talk about that is happening. So we also said that these two papers, revisiting RowHammer and trespass, revived let's say JEDEC. JEDEC is a standards body that standardizes memory, essentially, or memory interfaces, and also what goes potentially into those interfaces. What can the memory controller designers or chip memory people who buy memory assume about the chips that they're getting, right? So they talk about a lot of these things, and these two papers had huge impact in reviving the task group that essentially was kind of dormant because of the claims that are made by manufacturers. So they actually started doing work, and they put out these papers, and eventually they put out some standard mechanism or standard framework to solve RowHammer, which is essentially the per-row activation counters, which I mentioned. We're going to get to that. But before, again, summarizing what we did last time, we talked about reverse engineering more. We were able to reverse engineer essentially everything by having a clever side channel using the retention failures that you get, or the lack of failures that you get, as an indication that there's some internal refresh that has happened in DRAM. And I really like this actually, because this kind of ties together two big directions that my group has been working on. We tried understanding retention times a lot for more than a decade. And we tried understanding RowHammer a lot for more than a decade also. This kind of puts together these two in an interesting way, connects them in an interesting way. By using the understanding that you've developed for both, especially retention failures, you can figure out what's going on internally inside the DRAM chip. There's a lot that goes into it. It's not that easy, but if you're interested, you can read the paper. this methodology is being employed by many papers right now to figure out what's going on. There's actually a paper in Usenix Security, for example, that uses this methodology to show that DDR5 has bit flips also. Essentially, you can have RowHammer bit flips in DDR5, but they use this sort of methodology to actually show that. Okay, so we said that you can reverse engineer a lot. And we were talking about more analysis on RowHammer characteristics, and this is the last paper that we covered. This paper basically also does detailed analysis of things that are not examined as much in RowHammer and find some interesting results, like temperature. We still don't understand, as I said. So there's an open opportunity here to really understand what's going on with RowHammer versus temperature. And then aggressive row active time. This led to the row press work that I'm going to talk about, which is a completely different vulnerability, it turns out, and spatial variation, which led to the spatial variation work that Giray did later on. But basically, this is the summary of that work, which we discussed last time. If you understand more about where a RowHammer bit flip, or when a RowHammer bit flip, or how a RowHammer bit flip is more likely or less likely to occur, then you can actually use this as for building better attacks, more effective, faster, harder to detect attacks. Or you could do this for crafting more effective and more efficient defenses, basically. So understanding is actually good for everyone in the end. And if the attacker understands things much better than you, then you have a problem. It's good to think about that, you know. That's why open research in security and understanding vulnerabilities is really important, because that levels the playing ground, as we have discussed in the past, right? Because otherwise attackers may invest a lot to understand, whereas you're twiddling your thumbs and doing nothing, right? And then the attackers will be gaining access to your system, right? So it's good to think about this. Okay, and this is Giray's talk about that deeper look. This is where we stopped last time. Any questions so far? That's kind of a summary of the 2-hour lecture. No questions? Okay. You can ask more, but there's more RowHammer analysis to be done. We did some of it. This is actually a very nice paper, in my opinion. This is a DSM paper that we wrote. I'm not biased, clearly. So it's our babies, right? How can you not biased with your baby? Anyway, I'm biased, of course, but I'm also not biased because there's a lot of work that went into it. This is also Giray's work. But basically, the idea is to understand the effect of word line voltage, meaning if you change the word line voltage, how does that affect RowHammer? The theory is that if you increase the word line voltage, you would cause more disturbance to adjacent cells, adjacent rows, because you're really causing a lot more voltage swing across your word line. This is increasing all sorts of electromigration problems, crosstalk problems that are really fundamental causes of RowHammer. And we wanted to understand that, but theory is theory, but can you measure it using real DRAM chips? And that's what we did. Giray showed that if you actually reduce the word line voltage, you can reduce the RowHammer vulnerability, which is good. That is as expected. And the reduction is not huge. There's some maximum reduction, which is good, but on average, the reduction is not huge, meaning that this cannot be a solution to the problem by itself. And also it creates some other problems, which is reducing the voltage actually increases latency because you have less charge or less voltage to deal with. As a result, you cannot operate things as fast. So we've quantified that also, which is good. Reducing the voltage, unfortunately, reduces data retention time as well. But you can actually use some error correcting codes to fix that and maybe double the refresh rate for a very small, well, not very small fraction of DRAM rows. So you can fix these problems. You can also fix the activation latency issue. You can actually increase the latency, row activation latency, for those parts of a chip that cannot work reliably with the reduced voltage. So you can fix those problems. If you fix those problems, you reduce the RowHammer vulnerability without significantly affecting reliable DRAM operation, but this comes at a cost. Meaning you need to actually increase latency and increase refresh for a small fraction of parts of a DRAM chip. This is actually interesting to look at because this, in my opinion, this shows the difficulties that DRAM manufacturers have. It's not an easy problem to solve, basically. You can say, oh, when we actually first submitted our paper, it got rejected because one of the reasons was RowHammer paper, not this paper. Original RowHammer paper got rejected because one of the reasons was basically, oh, this problem should be solved by DRAM manufacturers. This is a comment that is very uninformed, in my opinion, because it doesn't understand the difficulty of low-level solutions to the problem, right? And the difficulty, I think this paper nicely shows one of the difficulties. Okay, you have one solution that sounds reasonable, increase the voltage. Yes, it reduces RowHammer vulnerability. It doesn't eliminate it, but it causes a lot of other issues, right? DRAM design is actually an art where you need to deal with a lot of things: retention, RowHammer, latency, energy, bandwidth, how do you use your error correction budget, etc. So there are many things, and if you change one thing, that affects all of those many things, right? So it's very difficult to do this design in the best way. So there's more to do in this area, I think. And I think this is a good starting point to understand the trade-offs in DRAM design in an experimental way, because we actually test real DRAM chips to look at the effects of how you trade off between voltage, RowHammer, latency, and retention time, right? These are actually 4 different points if you think about it. Okay, that's why I like this paper. And this is a talk by Giray on this topic. So as I said, we actually tested HBM chips. This is Ataberk's work, and we showed that they're similarly very vulnerable. You can read more about that in these papers. I'm not going to go through every paper, otherwise we'll be here until the end of next week or something, which nobody wants to be, I guess. But let's switch gears a little bit and talk about attacks and solutions. There's more understanding that needs to be done, and I'm going to talk about that. I'll keep switching gears between understanding and attacks and solutions, because that's fun, I think, because some of the understanding comes later. Some of the attacks and solutions come interleaved. So there's more understanding that needs to be done. But some of the understanding can be coupled with attacks also. There's a paper that was written, well, initially it was a security blog by Google. These folks discovered an effect in DRAM that was not reported before. They called it half double. And the problem is essentially, basically, a classic RowHammer has 1 or 2 aggressor rows, double-sided, one-sided. Let's take a look at one-sided here. You can do the double-sided attack also, generalize it. In classic RowHammer, you hammer one aggressor row many times, and you get bit flips in immediately adjacent, physically adjacent rows, right? Victim rows. Now they discovered that you hammer an aggressor row A many times, and then physically adjacent aggressor row B you hammer a little bit, not as many times, maybe 100 times or so. You get bit flips in the next physically adjacent row, victim C. Okay, so this is interesting. Basically, you don't have this aggressor affecting this victim immediately. This aggressor coupled with this other aggressor that you actually activate a little bit, not too many times, you get bit flips in this victim. Okay. Now this is interesting because of multiple reasons. One is certainly there's some device level problem that is causing this victim to be affected by both aggressors. And this is the main aggressor, this is the weaker aggressor, let's say. Now there's a bigger realization here, which is if you have a mitigation mechanism that detects this aggressor A and refreshes aggressor B, now that refresh, that mitigation itself can induce bit flips in the victim, right? I think that's cute. Because now you designed a mitigation thinking that you solved the problem, but the mitigation itself is becoming an attack on the victim row. Because if you do that enough times, and they've shown that you could do it enough times, and mitigation mechanisms can become an attack. Right? So that's the sad part over here, and that's a nice discovery, I think. And Google, this is annoying. What do I need to do? Maybe Seguras can help. Oh, okay. Okay, I see. Well, there's this one. Okay, let's see. No, it's okay. I can see it, but let's keep this. So basically, they called this the half double attack, and they published a paper in Usenix Security together with some folks to show that they can actually take advantage of this to essentially do RowHammer attacks. It's interesting. You can see that also the level of interest from major companies is big because Google developing attacks on DRAM chips sounds very interesting, right? This doesn't normally happen, basically. Okay, so any questions? Okay, so Microsoft also did a lot of work in this area, and they also published a lot of works. This is one of the works that they published, which is also interesting. Here, they basically showed that, I'm not going to go through the details of this, but they basically showed that even non-malicious code can cause RowHammer attacks because of some coherence protocol difficulties, or coherence, how the coherence protocol works, basically. You get a lot of, essentially, hammering to a row in these workloads. And they were able to show that you could actually reach activation rates for some rows that are larger than the RowHammer thresholds. So that's actually interesting work. Coincidentally, this is actually something that was known before, because the first, let's say, in the field discovery of RowHammer was based on a bit flip that was reported to Intel in some workload that did essentially something very similar. So we're talking about 2010s right now. So these people rediscovered kind of what you can do, what could happen in the field that actually happened 12 years ago. Which is, I think, good, because people should report these things, right? As opposed to these things being in closed doors and nobody knows about them, right? So I like this one, but there's a bigger story in this, as you can see, right? It was known, but it was known to a very small fraction of people, let's say. Okay, so we developed some more solutions also. This is the BlockHammer solution that Girai developed as part of his thesis also. Intel thought this was very useful, so they gave it an award. But the basic idea here is really throttling. This is the first throttling-based solution that's practical, I would say. And what we wanted to solve with this work was scale the solution. We want a solution that's scalable to very small, very bad RowHammer vulnerabilities, let's say. You get bit flips after 1,000 row activations, for example. And then the second thing that we wanted to have is we didn't want to change the DRAM chips. You could argue that limits you. Yes, that limits you, but still, if you can develop a solution that doesn't change the DRAM chips, you could implement it in the memory controller. That could be an okay solution, right? So we wanted compatibility with commodity DRAM chips without any changes, without requiring any information from the DRAM chip, and without requiring any change to the interface or the hardware of the DRAM chips. So this solution satisfies both of those properties at the time, because scalability is always a challenge, because RowHammer is getting worse and worse. Essentially, the idea is basically, if you have a lot of hammers going to a particular row, you detect using Bloom filters that a row is being hammered too much. There's a counting Bloom filter. So how many people know what Bloom filters here? A lot of people? Who doesn't know about Bloom filters? I think we discussed this. Did we discuss it? I don't remember now. So Bloom filters are essentially approximate data structures to represent set membership. Now, what does this mean? This is actually, it was developed in 1970 by Burton Bloom. And the idea is, if you want to represent whether, let's keep this example, basically. You want to figure out whether a row is being hammered. Whenever you access a row, you increment a counter that's hashed. Basically, you have a hash, you have an address, you have the address of the row. Whenever you activate it, you go through a hash function, and you increment a counter associated with that hash function, right? But you don't have as many counters as number of rows in the entire DRAM, because that's a lot of counters, right? We don't want that. You want to have a small set of counters, and we want to map addresses to these counters using a hash function so that they're distributed across those counters. Now you can keep track of how many times a row is activated approximately by essentially incrementing the counter associated with a particular row address going through this hash function. Now, the upside is your hardware is much smaller because you don't need a counter per row. You actually can decide, I have only 10 counters, right? Maybe not a good idea, but 10 counters. Now, the issue is that there's aliasing in the Bloom filter. Multiple different addresses mapped to the same counter, so they increment the same counter, right? This is okay in this particular case, because what we're going to do is we're going to say if the counter is greater than some threshold, this row is potentially going to cause a bit flip, Now, if the counter is incremented by only that row, you have an okay and exact count, depending on your limitations of the counter, etc. But if the counter is incremented by two different rows that are being accessed, you have an inflated count, right? And that inflated count may cause you to wrongly detect a row to be an aggressor. But that's not bad. You're conservative in that case. It may be bad for performance, but it's not bad for correctness, right? So you essentially have false positives or false increments in a counting Bloom filter. But that's okay for correctness. It's bad for performance. But you can actually design the Bloom filter to minimize performance impact, etc. So there's a lot of design choices that you can have. The takeaway is a Bloom filter can be much more area efficient than having per counter, a single counter per row. Okay, that's the idea. I like this sort of solution because it's not essentially, oh, we have a single counter per row and we increment it and the solution is done. We're going to get to that, but this is a more, let's say, creative, innovative solution. Now, once you have a counter associated with a row, and there's more implementation detail over here. If you actually, it turns out if you actually use only a single set of counters, it's not good. There are also issues like how do you reset the counters? Can you reset the counters safely? There are a lot of problems over here actually that you need to solve. But assuming that you solve them, which is done in this paper, when you get a counter to be greater than some value, the RowHammer solution says, don't access that row until we're safe. Okay, that's the idea. This doesn't require any information from the DRAM chip. This doesn't require you to know which rows are adjacent to each other because you're not refreshing anything. You're just stopping access to the row that you think is an aggressor. That's the idea. And you can configure this such that you're safe, bit flips don't occur. And also there are other benefits to this. We said that in the paper. We actually developed some metric called RowHammer likelihood index. And we measured that with attack. So the memory controller can actually measure this RowHammer likelihood index. And if the memory controller thinks that some addresses are being accessed, it can report to the system software that, oh, this particular program is accessing these addresses that are likely to be RowHammer attacks. And then the system software can do something about it. So this actually has implications that are actually very useful in my opinion. And most importantly, it's compatible with commodity DRAM chips. There's no need for proprietary information and modifications. And we show that this outperforms many solutions. And it's also more scalable and hardware, not as hardware intensive as some solutions. So it's good to think about these solutions. This is 2021 though. But this, you can see that now this is a more intelligent memory controller, right? It's not as simple as probabilistic adjacent row activation, which worked, but it doesn't work. This was able to scale to 1,000 RowHammer activation count of RowHammer threshold is 1,000 or so. But if you go below 1,000, the solution becomes more expensive. It doesn't, in terms of performance overheads. So now I'm giving you different solutions that look like this. Both have improved over time. We have another work called RowHammer, for example, on proactive throttling, but I'm not going to go through that. Any questions? Okay. So let's talk about industry solutions, more recent industry solutions. As I said, industry started taking this more seriously, and this JEDEC group came up with a framework that's very similar to what was published by SK Hynix in the circuits conference. This is ISSCC, a major circuits conference. And SK Hynix published this paper before JEDEC actually announced their changes. And this is the first paper from a major DRAM manufacturer. SK Hynix has the second largest DRAM market share. They actually, are they better than Samsung these days? Looks like they are. Okay. Okay, yeah. Basically, they do a lot of HBM. I think they were able to capitalize on the HBM manufacturing really well. As a result, maybe they're they're more profitable than what used to be the more dominant manufacturer. And essentially, this is the first paper that acknowledges RowHammer with that wording also. It's an interesting paper. It's very short. There's not much information in it. They basically talk about how they developed a solution to RowHammer. And the solution is essentially an intelligent memory controller inside the DRAM chip. They call it PRHT, per RowHammer track. So as I said, every row has an activation counter. And You can see the counting cells, etc. This is their picture. I didn't add any annotation. This is their annotations and their slides, maybe even the paper, actually. Basically, essentially, they have counting cells per row, and they're implemented in some way as part of the DRAM subarray, so they change things. And they describe how they don't describe exactly when things are incremented or decremented, if they're ever decremented, or when things are reset. But they basically say they keep an activation count, and when that activation count is greater than some threshold, they take some mitigating action, probably some sort of reactive refresh. But they don't say how many rows, etc. they refresh. So there's a lot of, let's say, information that's missing to, let's say, trust things very well. But the good news is I think this is a solution in the right direction, meaning this is what we've been arguing for many years. I mean, solutions were in the right direction, but this is actually a more sophisticated controller in the DRAM chip. Right? DRAM manufacturers were very cost sensitive, so they didn't want to implement anything inside the DRAM chip, but they put this inside the DRAM chip. I would actually argue that it's not the best solution. It's expensive, in my opinion. You could do better with bloom filters, etc., all of those other solutions, but the fact is that there's an intelligent DRAM controller inside the DRAM chip. They prototype this and they report some numbers. I don't know what they show, but basically, I think you can read this. This comprehensive scheme leads to a reduced probability of failure due to RowHammer attacks by 93.1%. And they have some mechanism to improve retention time. I don't know what that means, but it's very nebulous in terms of what things mean. These ISSCC papers are very hard to trust in general because they're two pages and they don't give much information about what they've done. You know, later people expand their papers to journal of solid state circuits. Those are easier to, but these guys didn't expand their paper. Okay, anyway. So Samsung also developed some solutions. This is one of their papers, which is interesting. It's a more probabilistic solution with some counting mechanisms. It's a bit hard to understand, this paper, unfortunately, but you can take a look at it. Unfortunately, it's not a secure mechanism. There's a paper that Google wrote that showed that this is not a secure mechanism. So maybe I'll flash that paper also. Google wrote a paper debunking, basically, Samsung's paper, right? That's also interesting, right? There's a lot of interesting stories in this world, in the DRAM world. This doesn't normally happen, you know. Okay, so this solution from Microsoft, actually, per RowHammer tracking, builds on this work also. Microsoft was developing not only attacks and analyses, but also solutions. And they published this work at DRAMSec in 2021, DRAM Security Workshop, which we organized last year. I think I flashed that. Maybe I'll flash that again. But essentially, this is also a paper that proposes per row activation counters and a very high-level sketch implementation of it. So these solutions influence the standard in the end. And in the standard, there's a framework that describes, this is the DDR5 standard. But I think all major DRAM standards will have something of this sort. They call it PRAC in the standard, per row activation counters. And essentially, it's the same idea that builds on the per row hammer tracking and also Microsoft's Panopticon. You have per row activation counters. The issue is the standard is generic, but it's better than the earlier standard, which said target row refresh. And target row refresh didn't really mean much. One of the issues here is at some point, the DRAM chip needs some more time to do mitigations, right? Because if you think about it, this is an in-DRAM solution. Inside the DRAM, there's some tracking going on in terms of activation counters, and the DRAM chip needs to refresh some adjacent rows, but it may not have time to do that because of the tight control by the memory controller to the DRAM chip. So they actually changed the interface slightly, not exactly, but they introduced something called alert backoff. So basically, the DRAM chip can raise the alert signal, which is actually used for error correcting codes, like some major problem in DRAM, such that the memory controller stops accessing DRAM for some time, basically. So there's some standard change that happens, which I'm not going to go into. If you're really interested, you can read our Kronos paper, which is much less cryptic than the JEDEC standard. But basically, they needed to change some things in the interface also to make this really work. I think they lost an opportunity to have a bigger change in the interface, which I'm going to talk about. We actually talked about that in the memory-centric computing lecture. Okay, so the question always is, are solutions good, right? I like this picture. So this is solving a problem that probably can be solved in a better way. Okay, so we actually evaluated the solutions after they came out, and we published this paper in DRAM-Sec and showed that it's even if you perfectly configure this per row activation counters, meaning perfectly safely, you need to basically determine thresholds exactly, RowHammer thresholds. You do all of that. Even then, you need to be careful in terms of making it secure, and you need to be careful in terms of making it high performance. Basically, one of the issues is incrementing the counters, the way they implement it or the way they suggest it. If you implement it not so carefully, you increase the latencies. And in the standard, this DDR5 standard, they basically change the latencies to increase. Some of the latencies increase because you need more time to increment these counters, right, internally inside the DRAM. And that turns out to be not so good in terms of performance. And we reported some average performance hits, meaning downsides of 5% or so in this paper. And we proposed solutions in some other papers, like this Cronus paper is actually a longer version of this DRAM-Sec workshop paper. Here, we basically proposed some solutions to have a separate subarray to have store the counters in DRAM and do things in parallel, so that you don't need to increase the latencies in DRAM. That's the idea over here. It comes at more cost, of course, because now you actually need to have a subarray dedicated for storing counters, assuming this is the solution you want to implement. That's what we're not claiming this is the best solution. Per row activation counter is the best solution, but assuming this is the standard solution that you want to implement, there are much better implementations than increasing the latencies for incrementing the counters. And I recommend you take a look at it. I don't know if anybody selected this paper. I don't think so, but this is one of the state-of-the-art works in this area right now. Okay, the question is always, can we do better, right? And you can always do better. I think there will be some papers that will come up that do better. But I think a better way is really designing the DRAM interface in a better way. So I'll go back to this paper that we discussed in the memory-centric computing lecture. If we can make DRAM much more self-managing and much more autonomous, then we don't need to deal with like a limited interface. And you remember this, so I will not go through this in detail. The idea is if the DRAM chip can do its own maintenance, and while it's doing some maintenance, like counter activation or counter, not counter activation, activation counter increment, or something else like refreshing the adjacent rows when the counter is greater than some value. All of those computations, at fine granularity, it can do these operations. And if for some reason at that point, the memory controller needs to access that particular portion where it's doing maintenance on, the DRAM chip can say no, basically. That's the idea. Have a negative acknowledgement at fine granularity. And this negative acknowledgement changes the interface a little bit, but it gives a lot of freedom to the DRAM manufacturers. That way, they can actually design their mitigation mechanisms internally. They can do a retention-aware refresh, etc. They can do many, many ideas. They can implement many, many ideas much more easily. So the way it was done in the DDR5 standard is a little bit bad. It's not like what we proposed, actually. It was essentially, you cannot access the DRAM chip while that's going on, right? This alert backoff. So it's a very heavy-handed solution. You need a much more finer-grained solution so that you don't destroy performance. And we showed that, actually, if a RowHammer attack can induce a lot of alert backoffs, your performance becomes much worse, right? And at low RowHammer thresholds, you will get that alert backoff. So disabling the entire DRAM chip so that it can do RowHammer maintenance is not a good idea. And this is demonstrated many times. So, but disabling a very small fraction of the DRAM chip while maintenance is being done in that area and enabling the memory controller to access all of the other possible areas where maintenance is not going on is a much better solution, as we have demonstrated over here. And the cost is not that much. And once you do this change, once you make this change, you enable actually a lot of other independent improvements inside the DRAM chip. The cost, of course, is, I mean, there's some cost, negative acknowledgement. Those are not big costs, I think. The cost is, of course, now the memory controller loses complete, let's say, dictatorship. It's not a dictator anymore. It cannot dictate everything. It's essentially, there's some things that are not under the control of the memory controller. Right? And maybe some people don't like that. Right? It also changed the design of the memory controller a little bit because you need to deal with negative acknowledgement, which is not that hard to do, as we have shown in our papers. But losing control of the memory controller is something that I guess memory controller manufacturers don't necessarily want. So it's good to think about it. There are business reasons why some really good ideas may not easily get implemented, but that doesn't mean that people should not be developing those ideas and demonstrating their benefits, right? Okay, so we demonstrated that you can actually do better DRAM refresh, better RowHammer protection, better memory scrubbing this way. And you know the story. This was rejected many times. Okay, I'll not go through this again, but this is not fun for PhD students. How many of you are PhD students here? Some of you? Okay, good to see. Okay, but we need to define business as usual, because if business as usual becomes science, then science dies. Right? That's why we need to actually show that. We need to also educate the reviewers to not reject the sort of ideas that may not be immediately implementable, right? Okay, for people who are doing research like PhD students, be resilient. Okay, so we also kept asking the question, like, are we bit flip free in 2024 and beyond? And it's a good question to ask, basically. Sometimes people claim that we're RowHammer free, and they use that to reject papers, which is not good. But we were also very interested in like other bit flip mechanisms. So until 2023, RowHammer was the only known read disturbance bit flip mechanisms. And we changed that in 2023 with RowPress. I've given you very briefly in the memory-centric computing lecture, but I'll go into more detail. This is a paper that was published at ISCA like 9 years after the RowHammer paper. And basically, it's a new disturbance mechanism, read disturbance mechanism. It's different from the RowHammer vulnerability. We've shown that. And also later works at the device level have shown that. And we showed that you could actually induce these RowPress bit flips using a user level program on a real system as well. And we provide some solutions to RowPress. And basically, this builds on a deeper look paper in Micro 2021, where we showed that if you actually keep the row active a little bit longer, this induces more read disturbance. At that time, we didn't know that this is a different kind of read disturbance. Basically, we thought it was an extension of RowHammer. RowHammer becomes a little bit worse, or somewhat worse, essentially, if you keep the row open. But in this paper, we showed that there's something that's fundamentally different from RowHammer. If you keep a DRAM row open for a long time, this causes bit flips in adjacent rows. They don't require many row activations. And in some cases, only one row activation is enough. This is if you violate the timing standards. Like if you keep the row open for 30 milliseconds, which is not allowed. But this shows that there is a fundamental problem here. You're not hammering, you're activating once. And that is actually causing a bit flip if you wait long enough, or if you keep the row active long enough. Active mean the row is in the row buffer, basically. So this is the picture that I've shown you in the memory-centric computing lecture. Basically, RowHammer, the assumption is that you keep activating the row as frequently as possible as allowed by the standard. In RowPress, you keep the row active as long as possible, let's say, as allowed by the standard. And the standard actually allows much longer than 7.8. I'm going to show you that one. It doesn't allow 30 milliseconds, but you can reduce the bit flips, reduce the number of activations to induce a bit flip by a lot if you follow the standard, and you can reduce it to only one if you don't follow the standard. Okay, so we used our FPGA-based testing infrastructure, DRAM Bender, which you've seen pictures of. This is another picture of it. And we tested essentially chips from all DRAM manufacturers. And we found that this is present in all chips that we've tested. And we showed that it's RowPress significantly amplifies DRAM's vulnerable to read disturbance. And it also has a different underlying error mechanism. We didn't know exactly what that mechanism was because nobody reported this problem before. There was no device level paper on this topic. So the paper is actually at the device level to really understand what's going on and why these bit flips are happening came later. After some folks read our paper, they basically developed a theory and they simulated in the circuit level and device level to really demonstrate why RowPress is happening and why is it different from RowHammer. So this is actually interesting because normally technology development happens by understanding the technology really well, right? The normal way of development is you develop some materials and then you build devices out of them, and you build logic, you build circuits and logic, and then you go to the system, right? Here, we have a system based on some old technology, DRAM. It's pretty old. And we're figuring out something that no one has reported, right? That's the fascinating part, right? With this sort of infrastructure, you can discover something that no one knows about. And the understanding at the device level comes later, right? We have some more things related to that will come up. Okay, so this is a summary of the results from the paper. Basically, these are three major manufacturers, I guess Samsung, Hynix, Micron. And you can see that this is RowHammer, which is you keep the row active as little as possible. And then if you keep the row active by 7.8 microseconds, you have a lot, you get to bit flips a lot earlier, meaning at much smaller activation counts. You can see an order of magnitude difference over here. And if you keep the row active 70 microseconds, which is allowed by the standard actually, you get an order of magnitude more. And if you keep the row active 30 milliseconds, you get only one activation. You can have actually only one activation to induce a bit flip. But if you are following the standard, then you can reduce the activation count to induce the first bit flip by 1 to 2 orders of magnitude. So that's fascinating, right? It's a fascinating result. So basically, you can greatly reduce the number of activations to induce a bit flip. And the number is actually really fascinating. So this is, if you keep the row active 7.8 microseconds, this paper reports that you can induce a bit flip after 380 activations. That's not a lot, but you need to keep the row active for a really long time. Still, it's possible to induce a bit flip. If you keep the row active in HBM, there's a later study that builds on row press. In HBM, you can actually induce a bit flip after 335 activations. Now, if you keep the row active even longer, 35.1 microseconds in HBM, you can get a bit flip after 123 activations. And in DDR4, you can get a bit flip after 51 activations. Those numbers are really low. The trick is, of course, you need to keep the row active long enough, 70.2 microseconds. Not so easy with today's memory controllers, because today's memory controllers close the row after some point. Right? You need to do some tricks. Okay, but these are real DRAM chip results that show that the vulnerability is actually pretty bad if you can keep the row active long enough, right? Okay, so we've already shown this. So this gets worse as temperature increases. This is an indication that row press is very different from RowHammer, because with RowHammer, we did a lot of temperature studies and we couldn't find a good correlation, as I discussed. Individual cells have different vulnerability windows, but different cells are all over the place. So in the end, as temperature increases, you have no correlation aggregated across temperature and vulnerability to RowHammer. Whereas here, you have a very strong correlation. As temperature increases, row press gets worse. Also, we've shown that a different set of cells are affected compared to RowHammer, which is also an indication that this is a different phenomenon. And also, it behaves differently with access pattern and temperature. Well, temperature I said, but access pattern also, that I'm not going to go into. So we basically did as much as possible our due diligence to show that this is a different effect. And we called for research to really understand the device level mechanisms more. Another thing that this paper did was to show that on a real system, you can induce these row press bit flips. And the idea is to write a program that keeps that basically pushes the memory controller to keep the row open as long as possible, right? And how do you do that? Basically, you keep accessing the same row. And again, how do you do that? By accessing consecutive cache blocks in the same row. You're hoping that these requests are actually going to the memory controller, and the memory controller keeps the row active so that it can exploit row buffer locality. So existing memory controllers try to exploit row buffer locality. If there's an access to the same row, they don't close the row. They try to service those accesses that go to the same row, because closing the row and reopening it is expensive. So they try to maximize row buffer locality. And we've seen that actually, if you do this, at some point you start getting bit flips. These are the number of cache blocks per aggressor row activation. And if that number is larger, you get bit flips. And we were not able to induce RowHammer bit flips on these chips that we've tested. And the number of rows with bit flips also increases. It's not just the total number of bit flips, but also number of rows with bit flips also increases. So we basically declared victory, saying that you could actually induce this on real chips, on real memory controllers as well. So the question, of course, how do you mitigate this? So I think we proposed 4 mitigations. We described one of them in more detail, but one mitigation is, of course, changing the DRAM chip somehow, such that a row doesn't become active too long, right? If you decouple the row from the row buffer, that could be one solution. That introduces some downsides, but it's possible to do it. I think there's more work to be done in that area also. But what we have suggested is really you have developed some RowHammer solutions, but RowHammer solutions don't work for RowPress because they don't take into account the additional vulnerability that happens because you kept the row open, right? So we suggest a methodology for adapting existing RowHammer solutions. It could be any RowHammer solution, actually. And we showed with Para and Graphene. Basically, we said that to make this easy, have a maximum row open time limitation in the memory controller. Now, if you actually set this maximum row open time to a very low value, you exploit less row buffer locality, right? If you set the maximum row open time to a high value, you cause more disturbance, essentially. So you set it reasonably. You lose some performance because of that, but if you set it very carefully, maybe you don't lose as much performance. You don't want to set it basically every access close the row. That's terrible. And you configure the RowHammer mitigation to account for row press induced reduction in activation count to induce a bit flip to that maximum row open time, essentially. So you make your RowHammer mitigation more aggressive, essentially. So this is a methodology to adapt any RowHammer mitigation. And we show that it works for Graphene and Para. It introduces some additional overhead, as you can see. We declared it low, but it may not be very low, depending on the vulnerability and your configuration. But essentially, that's the idea. There's a lot more results and analysis in the paper. You can find it. People have replicated these results both in industry and academia. They've actually built attacks on top of RowPress. There are RowPress attacks that combine RowPress and RowHammer, full attacks, and they also propose solutions, etc. This got the Distinguished Artifact Award at ISCA, so it's a nice artifact as well. It was also an IEEE micro top pick. People, when we first, if I get to that, how much time do we have? Let's see. Oh, I keep going. I said I was going to go slowly, but well, I was going to go less, but I guess let's see. So yeah, it was selected as an IEEE micro top pick, which is interesting. Yeah, because our original paper was submitted to this topic. So IEEE micro is a magazine that has this issue every year, where they select supposedly the best computer architecture papers of the year. And this got selected, but our original RowHammer paper didn't get selected because people thought that it had no impact. So it's actually interesting. History is the best rebuttal to reviewers, let's say. Okay, so these are the 2 papers that folks from Shanghai Jiaotong University wrote about in terms of the device level mechanisms. So these are actually very nice papers, I think, that discovered, based on the results that we shown, what's going on with RowPress, basically. What is the underlying physical mechanisms that lead to RowPress? How does it differ from RowHammer, etc. So if you're interested, you can read these papers. Or you can read Hao Song's paper, which is building on their work to demonstrate some open inconsistencies between experimental results that we have, as well as the device level results that were published so far. So there's some discrepancy that we don't quite understand right now. It's good to report these things so that people can have more accurate models at both at the low level, so that low level solutions can be better as well. So as you can see, this is fascinating, right? And these folks didn't work with us at all. They basically read our paper. They said, oh, I guess they said we should come up with a way of figuring out how this works, and they figured it out. Okay. So there's more to come, I think, in this area. So I think there's, we're getting closer to the end, but there are 2 major directions that are really interesting going into the future. I showed the slide before. Essentially, we need to understand more, and there's a lot more to do. And we need to understand certainly memory errors, but also hardware errors in general. These days, people are talking about silent data corruption, for example. There's silent data corruption going on in CPUs also. I think that's also interesting. But memory is much bigger fraction of the hardware that we have, and there's more to be investigated in memory as well. There are many effects on bit flips that are still not rigorously examined. Aging, for example, aging effects are very difficult to examine. We tried it so far unsuccessfully. There's more to do in that area to understand the effects of aging. And some of these things are very difficult to simulate. And if you simulate it, it's very hard to necessarily believe the results of simulation, because aging is such a difficult topic that it's not easy to basically understand what happens. So there's more to do in this area. That's easily a thesis, basically, aging of DRAM chips. Environmental conditions, there's still more we don't understand, especially in temperature. But maybe there are other things like radiation, humidity, especially if we're going to use these things in space, for example. These days, for some reason, everybody's excited about space. I guess they're planning to evacuate this Earth for some other reasons, maybe. But yeah, space is very interesting, no question about that. I think we should be exploring it. But the current computer systems we design for space are so many generations ahead of what we do on Earth. Right? It's good to consider this discrepancy. And I think people who ignore computing when they try to go to space will have huge difficulties up there to the point of maybe they will not return. If the right people go, maybe it's okay. But anyway, that's a joke, of course. But basically, how do these chips behave under harsh conditions in space, right? It's good to think about that, right? Aging will be an issue over there because you may not be able to replace these things like you would do in a data center. People are talking about space data centers also, combining two concepts, right? And maybe space data centers need to be more careful, right? What kind of chips do you employ over there? How do you actually deal with these errors in space, etc.? Memory access patterns, memory control, and system design decisions, these all affect actually bit flips that you get. And some papers build some understanding, but there's more to do in really understanding how is a system designed and how does that affect the errors that you get from memory or some other part of the system. And then there's a solution space. This is understanding. Of course, understanding can inform the solution space as well as the attack space, but solving is also important. Like we need more flexible and efficient solutions. And there's more work in this area, which is good actually. And I think there's more work in co-architecting across the system stack as well. So we've updated our recent survey paper on this topic. We actually wrote a lot of papers saying that there should be more communication between the controller as well as the DRAM designers so that you can actually get to a better point in terms of design of DRAM systems. This is a paper that I would recommend if you're interested in looking at it. We talked about self-managing DRAM, but there are other controllers that are interesting. Abacus, I think somebody is going to present the Abacus paper, so I'm not going into detail, but we've developed some other solutions. This was presented by Ataberk at Genomic Security last year. So there are more low overhead solutions. This is a paper by Nisa Comet, which was presented 2 years ago at HPCA, that actually takes the hash-based, counter-based solutions to be more, even lower overhead, right? How do you actually keep track of rows using some algorithm that's hash-based? So this is actually a very interesting solution also. And there are solutions that exploit spatial variation. And this is the one that I mentioned before, that essentially improves RowHammer mitigations by very selectively throttling threads that can cause these RowHammer bit flips. And this also has a solution for reducing denial of service problem with RowHammer. So one of the issues with RowHammer solutions is you can solve the problem. It comes at a hardware cost, but it turns the problem to also a denial of service problem, meaning you basically call an attacker thread. Maybe if you configure your solution nicely, an attacker thread will not induce bit flips, but now it degrades performance for everybody else in the system, right? Because it's causing the DRAM to be slowed down, right? DRAM is other threads cannot access DRAM when the solutions are employed. So this paper throttles some of the suspect threads to actually reduce the performance impact of RowHammer solutions. Okay, and Nisa has done work on some of the side channel and covert channel vulnerabilities that are new, that are introduced by these RowHammer defenses. So whenever you actually come up with a new defense, that could also be a new attack. I like this thinking. It's whenever you're designing a system, this is like the half double, right? If you think about the half double work, that show that your defense may become an attack because they discovered a new phenomenon in DRAM chips. In this case, NISA showed that the mitigation mechanisms that you introduce cause essentially these refreshes, and they can actually be used as side channels and covert channels to communicate information about a malicious attack. So if you're interested, you can take. I don't know if anybody selected it, but it's an interesting paper to think about. So whenever you introduce a defense, you may actually introduce a new vulnerability also. It's good to think about that. Now, this is a harder vulnerability to exploit, but it's possible. Again, don't underestimate any vulnerability. It's good to report and analyze it. Okay, GI's thesis is a good resource also. I keep showing that, but this deservedly got many awards. It should have gotten ETH medal also, but I don't know what the ETH folks were smoking when they gave medals. It should have gotten, I think, for sure. Okay, there's more to come, basically. So the key question is, there's a lot we don't know about DRAM, actually. This is what's fascinating to me. This is a technology that's been around for 60, almost 70 years now. And we're still discovering things. The question, of course, is what else is lurking there that we haven't figured out yet? And this is really a scientific question also, because some of these things nobody has figured out. Even people who are designing these, let's say, chips, at least publicly, they don't know about it, but privately also, they don't know enough about it. For example, the fact that you could do these bulk bitwise operations in a functionally complete manner in DRAM chips, demonstrating that in a real DRAM chip has a huge value that basically opens the eyes of even the manufacturers who are manufacturing these chips. Right? It's good to think about this. So aging, I've discussed. We have some data indicating that RowHammer becomes worse with aging. This is data from GI's thesis and also the spatial variation paper that shows that after many days of continuous hammering, the RowHammer threshold reduces significantly. Another discovery was this paper. Again, we don't know the underlying reasons of this, but in Altaberg reported last HPCA that essentially the read disturbance threshold, the number of activations to induce a bit flip, changes randomly and unpredictably over time. Meaning accurately identifying this read disturbance threshold that everyone banks on to configure the RowHammer solutions with is challenging. So if you keep testing DRAM, you will find lower and lower read disturbance thresholds over time. This may not be a huge security vulnerability. It may also be, but it may be a failure mode that you can run into, especially if your chips are out there in space and you have no way of changing them, for example, right? So basically, this is a key problem. A read disturbance threshold varies unpredictably over time. And this is also a new discovery because we don't know the reason for it. There's no reported paper work that talks about it. And this makes also profiling for RowHammer even harder, basically, because if you keep testing and you get having lower and lower RowHammer thresholds, right? Now we have some hypotheses as to why this might be happening. It's somewhat similar to variable retention time phenomenon that we have discussed in retention time, but it's not clear if it's the exact same phenomenon. Probably not. Okay, more recently, Ismail has shown that there's actually a even worse vulnerability, column disturb, where a single row activation causes bit flips across thousands of DRAM rows. So across 3 DRAM subarrays. I think this paper may be presented again, so I will not go into a lot of detail. But the idea over here in one slide is by repeatedly opening or keeping a DRAM row open, it's possible to disturb many DRAM cells on the same DRAM column. So you're basically hammering this row. RowHammer says basically adjacent rows will be affected. We know that, that's RowHammer. But column disturb essentially says that whenever you're activating this entire row, you're perturbing all of these bit lines. You're perturbing this bit line because you need to sense the value over here. You're perturbing this bit line, you're perturbing this bit line, and there are other cells that are connected to that bit line, basically, and they get affected little by little. And also, some rows in the other subarray get affected because they're also, let's say, weakly connected but they are still connected. So this is the DRAM architecture today. You have a bit line, the value that you activate over here gets sensed by the sense amplifier, and then that sense amplifier is shared by the other subarray. So there are these blue cells that are also affected when you activate this row. So now you're really affecting thousands of cells, right? And we have shown that it affects up to 3072 DRAM rows. Now this basically cannot be solved with existing RowHammer solutions. Existing RowHammer solutions, well, I guess BlockHammer is an exception. Okay, with BlockHammer, maybe you can solve it. But per row activation counting, for example, is not a good solution because it doesn't take into account. Basically, it refreshes a few physically adjacent rows, right? It doesn't refresh. It doesn't think about even the other subarrays, right? RowHammer doesn't extend beyond subarrays. So the question becomes, how do you actually solve this problem? So this is actually interesting. There are multiple questions over here. First of all, why is this happening? We actually have a hypothesis, but there's more device level understanding that needs to be developed to really model it at the device level. That's not our expertise. Somebody else needs to do it. And the second is, how do you solve this problem? There needs to be a new family of solutions to solve this problem that need to be integrated with RowHammer solutions also. But maybe they're targeting these two things completely separately. Although BlockHammer is nice. Another reason to look at throttling-based solutions, right? Okay. And more recently, Ismail has also shown that if you actually do RowHammer and row press while using processing using DRAM, meaning multiple row activation, either simultaneous or consecutive, then you actually get even more bit flips. So you actually make the vulnerability much worse if you're doing processing using DRAM. So this is a question that we've been getting many times. Like if you're doing processing using DRAM, what happens to RowHammer vulnerability? And we have a lot of data to show that this becomes much worse. And solving this problem is not easy also. So these works actually show phenomena that are not completely understood at the device level. Sometimes they're not even understood or modeled. But they also open up areas where there needs to be more work done to solve the problems. Because Colon Disturb paper, for example, shows that this vulnerability is worsening. It may not be as bad as RowHammer today, but it's going to become much worse according to our scaling studies that we have done. So if something is not done about it, at some point you'll get bit flips. But at least now where the paper is published, then people will not be surprised if they get bit flips, if they do nothing about it. But the hope is that they will do something about it so that you don't run into a situation like RowHammer happened. And here, if you actually want to use processing using DRAM, then you need to be very careful about what happens to RowHammer, because someone can use those operations to induce bit flips much worse. Or maybe some programs will do it naturally. Because there are some, in some cases, you get only 23 simultaneous multi-row activations to induce a bit flip, for example. Okay, so it's interesting to discover these things. That's why we keep building the lab. There are other technologies that are interesting, but they all have their problems, as we've discussed. They all require intelligent memory controllers, like phase change memory, for example. We did a lot of work on phase change memory, STT-MRAM. These are very good to examine. Unfortunately, they all have some sort of problem that requires an intelligent memory controller, including RowHammer type of problems. Okay. So that's why I suggest people to follow their passion. There are a lot of naysayers that say nay and make toxic comments sometimes, but you follow your passion, and then you actually chart new territory that no one has uncovered. But this requires you to build infrastructure. We built a lot of infrastructure over many years to enable this. And sometimes taking the next step to show something new requires building a complete new infrastructure or another infrastructure that that does something that's not possible with current infrastructures, right? That's what these infrastructures have enabled for many years. And that requires hard work also. Maybe most importantly, it requires resilience, you know, because you will get toxic comments from reviewers at the very least. Okay, let me see. I can tell you that story, but maybe not today, because I do want to end early today. So when we actually first submitted the RowHammer, you can look at the slides. In the backup slides, you have some comments from the reviewers for original RowHammer paper that said that this is not an interesting problem. Manufacturers will solve it. We don't need a paper about it. They also said that one of the other comments to reject the paper, the first one was not to accept the paper either. One of the other comments was, the architecture community can do nothing about it. They did acknowledge the problem, but they said basically architecture community can do nothing about it. So we should not publish in architecture. Go publish in this lowly conferences that I don't need to deal with. Of course, I'm making it more, let's say, colorful. But they go publish at DSN, for example. Somehow they don't like DSN for some reason. But that's how it is, you know, and reject. So basically, we said that this is an architecture problem. And I think history has proven us right, because look at these architecture conferences. They're all publishing RowHammer papers, right? It's not only our RowHammer papers. Well, there's security conferences also. And there's even the reliability physics symposium papers. Well, that's normal, I guess. Okay, so these are some papers that I'm not going to talk about, but you can look more, I guess, more recent ones. We had a DRAM security workshop. You can take a look at it, where we had very good discussions. The next version is going to be at ISCA, a full-day workshop, so we'll have another one. And as I said, security folks are actually developing a lot of attacks also. Micro had a lot of papers. HPCA this last January had a lot of papers, as you can see. ASPLOS coming up, which I'm going to, has at least 2 papers. I don't look carefully because they have an interesting webpage where it's very hard to keep track of papers. I need to develop tracking mechanisms for tracking papers, you know. Okay. And IEEE Security and Privacy has some papers coming up also. Okay, let me talk a little bit more about the future, and then I'll talk about the past and we'll conclude. Basically, cells are going to become increasingly vulnerable to redisturbance and many other effects, perhaps. So it's good to discover them. And essentially, these may already be happening. We don't know what's lurking and slipping into the field, right? RowHammer clearly slipped into the field. Retention errors may have slipped into the field. My guess is yes, they're out there, but they're not as easily inducible as RowHammer. There may be other errors, so it's good to discover these things. And again, it's good to discover this as a white hat researcher to fix the problems before people who want to exploit these for profit or fun can do it. I guess fun may be okay, depending on the level of fun. But some people want to take over everything for fun. Okay, they tend to be the most powerful people in the world. Or institutions. Okay, so there's a lot to be discovered in main memory, DRAM, flash memory, emerging technologies. I think we should be looking at all of them. But clearly, DRAM and flash memory are very strong today, right? There was a time when these other technologies were being developed. It's become more difficult for them because DRAM and flash memory have been evolving also. People have tried to make things scale more and more. As a result, these emerging technologies are very, very interesting, but they have a hard time in replacing, at least in the general purpose domain, these technologies that are everywhere, essentially. DRAM and flash memory are everywhere. So emerging memories also need intelligent controllers, essentially. So we need to build more robust systems. And I think for this, I don't have a full solution, but there's a methodology. I think we need to really understand more. We need to develop methods for vulnerability modeling, discovery of these analyses. So if we can actually automate this process somehow, that would be nice. I don't know how to do that, but I think this needs to be done based on modeling and prediction that's based on real device data. So measuring real device data is really critical because some of these mechanisms are not even known, as I've shown with RowPress, right? You cannot even simulate it because you don't know that it exists, right? So, but we need a methodology to discover these things somehow. It may be basically continuous testing forever. That may be interesting, but that's expensive also. So it's good to think about this understanding part. Of course, once you understand, you can architect better. And I think having principled architectures like self-managing DRAM that partitions duties across the stack in a nice way is good. Having patchability in the field is good. And the key is you cannot give up performance and efficiency easily. And then I think we still need to develop more principled design, automation, and testing methods with robustness in mind, especially online testing methods, I should say, because things like variable read disturbance, for example, the read disturbance threshold varies and it changes over time. We don't know how it even behaves in space, for example, under radiation, aging, humidity, whatever. So it's good to have a mechanism to discover that you're at the brink of failure, or well, hopefully before that. And this requires, I think, a lot of testing methodologies, testing to be done by the memory controller online. Okay, that's why I think developing these methods using real device data, figuring out things is really important. That's why we keep developing this infrastructure. I'll go back to bridges. We start with bridges. This is the bridge that I showed you. Interestingly, human beings have been building bridges for thousands of years, right? And they still haven't gotten right. This is in Seoul in 1994. This is in Genoa, close to here. Wait, no, this is in Minneapolis. That looks more like Minneapolis. This is in Genoa. This is in Pittsburgh. So for those of you who are going to Pittsburgh, you can visit that area. It's not like that anymore, but I used to go over that a lot. Fortunately, not during that time. Yeah, it's a nice view, as you can see. Right. Anyway, so basically, in bridges, we have limited opportunities to fix things, right? It's very heavy infrastructure, but with memory, we have a lot more opportunity, right? We can avoid such failures by designing much more intelligent controllers, because we are dealing with something soft, right? We can actually design that memory controller to be much more intelligent, such that you can figure out that something is going to happen and it prevents that thing from happening, right? With bridges, it's a bit hard to do. You need to do your due diligence to maintenance, but sometimes there are catastrophic collapses also. Okay. So there's a big challenge and opportunity. So many more bit flip sources are to be discovered, which is fascinating. Let me give you some final thoughts, and then we're going to finish, because RowHammer is actually very interesting from many perspectives, security certainly, but also building dependable systems. And when we first discovered RowHammer, I talked to some very smart colleagues that I had at Carnegie Mellon. One of them was Satya. He did a lot of work on AFS and file systems, distributed systems in the past, basically. And he immediately took my paper and adopted it in his distributed systems class, which is very nice. That's basically cutting edge, right? That's how things should be in the cutting edge. Because this, for him, was a great example of Byzantine failures. Basically, this is a slide that I borrow from him now. And essentially, Byzantine failures are characterized by undetected erroneous computation. Right? That's the class of failures that people think when they design systems, distributed systems, and they try to protect against this. It's very difficult to protect against these. Redundancy, having a lot of redundancy protects against. Basically, you have erroneous computation, and you don't know about it. This is the opposite of what you really want in a principled system, fail fast. Basically, if you have an error, fail fast, either with an error or give no result, right? That's a good design principle for a dependable system. Now, the interesting thing with these Byzantine failures, people knew that erroneous is not just erroneous. It can also be malicious, meaning someone can exploit it. The only distinction is really intent. Right? The malicious person can induce a RowHammer bit flip and take over your system. So all of these were at some level known in a sense, right? Even the attacks on cryptographic keys in 1990s, people have shown that if you have a single bit flip, you can actually, your cryptographic protocols are broken because someone can recover your private key, essentially. So these Byzantine failures are very difficult to detect and confine. So do all you can do to avoid them. So this was a great example of a Byzantine failure for Satya, as you can see. By the way, he has a very nice keynote talk at Systor in 2020. You can take a look at it. That talks about some of the edge computing related things. How many people have read this paper? Nobody's a computer scientist here? I guess in computer science, people don't read papers anymore either. That's possible. Yeah, but this is a beautiful paper that introduces the Byzantine generals problem. And the idea is basically, maybe I'll read it very quickly, but I don't want to go into the details. Essentially, reliable computer systems must handle malfunctioning components that give conflicting information to different parts of the system. This situation can be expressed abstractly in terms of a group of generals of the Byzantine army camped with their troops around an enemy city. Communicating only by messenger, the generals must agree upon a common battle plan. However, one or more of them may be traitors who will try to confuse the others. Sounds nice, right? The problem is to find an algorithm to ensure that the loyal generals will reach agreement. It is shown that using only oral messages, this problem is solvable if and only if more than 2/3 of the generals are loyal. meaning they're not traitors. So a single traitor can confound two loyal generals. With unforgeable written messages, the problem is solvable for any number of generals and possible traitors. Blah, blah. So you can read it. There's a lot of work in dependable systems area on the Byzantine fault tolerance and trying to reduce the cost that was discussed over here if more than 2/3 of the generals are loyal. Okay, there was also some work that is really interesting that we knew about, which appeared at IEEE Security and Privacy in 2003. How many people have read this paper? Hopefully some of you did. If not, you should. Especially the PhD students here. Or do PhD students not read papers these days either? Okay, hopefully that's not the case. We don't want AI to do PhDs these days, you know. I don't trust them. The AI. I trust my PhD students a lot, but AI, they need to build that trust. It's not going to happen anytime soon, in my opinion. But anyway, this paper was published about 20 years ago, 23 years ago. And what these folks did was something fascinating. It's essentially Google's second attack, which takes over the Google native client using RowHammer. But they were able to induce memory errors in a machine, and they were able to take over the Java virtual machine at the time. So Java virtual machine provides a sandbox to programs executing under the virtual machine. Basically, you can get out of that sandbox and you can take over the Java virtual machine. And this is a beautiful paper. I really like it, actually. And the way they induced these bit flips was using this lamp. It sounds like a poor man's RowHammer, right? Now, the difficulty, of course, is it's not RowHammer. It's a physical. You need to have physical access to the device that you're attacking. You don't have that physical access that much. And basically, that limits the attack scope and the threat model a lot. But it's very interesting to see that. So this paper is actually published. It didn't have a whole lot of impact, but I thought it was very creative. Now, what RowHammer did was it basically replaced that. And of course, also, this makes the attack much harder because if you actually do this to memory, you'll get a lot of errors. You may not be able to succeed with your attack. You know, you want the errors in the right place. You don't want the errors everywhere. So they were able to show with some probability they could get this attack working. What RowHammer did was basically it replaced that lamp with essentially hammering mechanisms. So now a simple memory error that's quite predictable can be induced by software. Right? That's why RowHammer actually enabled a lot of those bit flip type of attacks that the security community did not develop after this, because it's very interesting, yes, but it's not a very practical type of attack, right? But with RowHammer, all of those attacks become much more practical right now. That's why RowHammer has a lot of impact on the security community. So I'm not going to talk about this because we kind of said some of this. Essentially, the fact that all of the real memory chips are vulnerable, and the fact that now you have a connection between reliability and security caused a new mindset in the security researchers. So they started thinking, oh, can I exploit this? They developed a lot of attacks. They and a lot of others have developed a lot of solutions. And there's more to come, I think, in this area. But the bar is becoming higher and higher because it actually inducing these bit flips in new chips. Like in DDR4, it was harder than DDR3 because DDR3 didn't have any protection. Now DDR4 has some protection. DDR5 will have some more protection. They will also have some in-DRAM error correcting code. So there will be multiple mechanisms that will make it harder to induce these bit flips. But people have shown that DDR5, you can induce these bit flips still. Now, if you actually have per row activation counters, it's going to be even harder to induce the bit flips. I don't think they will get all the corner cases right. So there will be some way of inducing these bit flips, but it will probably take a lot of time to induce these bit flips. But RowHammer solutions are still very good to develop, and trying to actually induce these bit flips is still good to do. And trying to understand the device level or trying to understand the vulnerability at a fundamental level, like testing in a lab, is still very useful because that can enable other vulnerabilities to be discovered. So essentially, RowHammer enabled a shift of mindset in mainstream security researchers. Essentially, they enabled them to think that general purpose hardware, which is in all computers, is fallible, right? And its problems are exploitable, and they were able to exploit it. And they actually started exploiting other things, right? So they started understanding hardware's inner workings and vulnerabilities, in some cases much better than architecture researchers, based on the comments that we received. And it's no coincidence that two of the groups that discovered meltdown on Spectre, which is actually side channel attacks in general purpose processors. They heavily worked on RowHammer attacks before. So they were inspired by the fact that RowHammer exists. Can we actually do something in real CPUs also? So there's a lot more to come in that area also, basically, how vulnerabilities in real systems. Okay, I think I've said a lot of these things, so maybe I'll say the good things a bit more. Basically, there's a lot more to do in this area. You will see from some of the papers. The good thing is, I think there's a lot more openness. Still not as much as we like, but there's a lot more openness to discuss in industry as well. And people are developing both attacks and defenses. It'd be good to enable them more as opposed to rejecting things. I'll acknowledge people who've done a lot of work in this area. Some of them are sitting here, but you can read more about them over here. Okay. And also a lot of people have supported this research, especially recently, Google and Microsoft. They've given us a lot of security and privacy awards to do a lot of research in security, privacy, and RowHammer, essentially. So that's good. Okay, I think we're done. But I will also mention that Remulator 2 has been very instrumental in doing a lot of studies of RowHammer. A lot of solutions are implemented in Remulator and Remulator 2. So you can actually, when you start RowHammer research, you're not starting from a blank slate. A lot of things are open sourced, either in the Remulator 2 repository or some other repository. So you can develop solutions using Remulator 2, and a lot of people are doing that today. Or you can develop new analyses using DRAM Bender, which is what we discussed also. By the way, DRAM Bender paper was rejected twice also. Architecture folks didn't like it. Now they use it. Okay, these are some courses that we have. We don't hold these courses anymore, but you can take a look at them if you want to learn more about RowHammer, DRAM, Remulator, and more emerging memory systems with Remulator. Okay, I'll stop here. I'll take any questions. If there are no questions, we'll end early. Any questions? Now, I think there will be at least 2 papers on RowHammer related things, right? Is that correct? At least 2? Is there a more precise number? Is it 2 or 3? Okay, 2. And there will be a bunch of papers on processing in memory. So we covered a lot of background on these topics now. We didn't cover those exact papers, but I think there's a lot of interesting discussions that we can have. In the upcoming sessions. It's an example of online error profiling and correction. I corrected the lecture number. The computers should be able to do that also, right? You do some of it, I guess. Oh, it came back. Is it shared right now? Interesting. I didn't know that. I shouldn't stop sharing. Okay. Going once, twice. No questions? Is this room better? Yeah, I see a lot of heads nodding. Who doesn't think this room is better? Oh, okay, sorry, yeah. Also, why are these blinds down? Somebody wants to be a bat here, I guess, but we need to fix that problem also. Okay, all right, we'll see you next week. Take care. Have a good weekend.